Until now in the two lectures we were considering the double integration problems where the strips were taken either parallel to x-axis or parallel to y-axis. When we considered some problems related to change the order of integration, we found that a few problems cannot be solved even after changing the strips, that is if the strips were given parallel to x-axis and if we choose them to take parallel to y-axis, still we could not integrate a particular function. One of those functions was, if you recall, it was log of x square plus y square. At the end we have seen the radial strips where we switched over from Cartesian coordinate system to the polar coordinate system. In polar coordinate system we have got a straightaway replacement, or what we call it as a substitution, that x will be replaced by r cos theta and y will be replaced by r sin theta. R is nothing but the distance of a particular point, that is x comma y, from origin, and it will be obviously under root of x square plus y square. Theta is the angle made by the radial direction, that is the line joining origin to that particular point x comma y, and the angle between this line and x-axis is considered as theta. When we make such a substitution, then the function in x and y will be changed to function in r and theta. Now the entire integral is to be rewritten because the elementary area that we were having dx dy will now be r dr d theta. The subsequent proof we have given through Jacobians, which is not every time essential, rather it is not part of our syllabus. Once we switch from the Cartesian coordinate system to the polar coordinate system, then the problem becomes simpler and the integration can be done easily. Let us consider the next problem. It is integral 0 to a sin beta, integral y cot beta to under root of y square minus a square minus y square. It is log of x square plus y square dx dy, where it is given that beta is in between 0 to pi by 2. We will start with our usual discussion. First of all, we observe that limits are in y. When limits are in y, these are going to be values of x. So we get x equal to y cot beta, which is the lower limit, to x equal to under root of a square minus y square, which is the upper limit. And the outer limits will be obviously values of y, that is y equal to 0 to y equal to a sin beta. Now when we consider these four curves, we understand that as the inner limits are in terms of y, which are values of x, we should be integrating with respect to x first. So we are required to integrate with respect to x first, into bracket, as strips are parallel to x-axis. But obviously the function is log of x square plus y square, which cannot be integrated with respect to x, and for that matter with respect to y also. We will first of all find out the region of integration from the four curves which we have already written. Out of that, the very first curve is x equal to y cot beta, which can be rewritten as y equal to x upon cot beta, which is nothing but x into tan beta. We find the similarity between this particular equation and the standard equation of line y equal to mx, which is passing through origin. And if you recall, m is nothing but the slope of the line, which is normally written as tan theta. So we find that this particular line, which is y equal to tan beta into x, is a line passing through origin, which makes an angle of beta with x-axis. So we can start with the region of integration. We will be drawing a line which makes an angle of beta with positive x direction, and this is our first line or a boundary, y equal to tan beta into x. The second boundary that we have is x equal to under root a square minus y square. Squaring both the sides, we get x square equal to a square minus y square, or x square plus y square equal to a square, which happens to be a circle having radius as a, center as origin. So we can draw that circle. With radius a, and so the boundary, second boundary, that is x square plus y square equal to a square, can now be drawn. The third boundary is y equal to 0, that is nothing but x axis, and then as we know that this radius is a, we can very well find out coordinates of point of intersection of the circle x square plus y square equal to a square and y equal to tan beta into x. This distance being a, we can simply find out these coordinates as a cos beta, which is nothing but x coordinate, and a sin beta, which is nothing but the y coordinate. Now from y equal to 0, the second limit we again have as y equal to a sin beta, and y equal to constant is always a line which is parallel to x axis, and so such a line in this case will be passing through the point of intersection, which also has got y coordinate as a sin beta. So line is y equal to a sin beta, and then if we see the sequence, then the inner limits are in terms of y, which are values of x, and the strip begins at x equal to y cot beta, that is on the straight line, and it will be always from left to right when the strip is parallel to x axis. So strip begins on this particular line and goes up to the circle. So this is how the strip is, and such strips are taken from y equal to 0 to y equal to a sin beta. Ultimately we find that the region of integration is something like this. Once we obtain the region of integration, then we can go for the radial strips, and for that we are required to convert everything in the polar form. Obviously the circle x square plus y square equal to a square can simply be interpreted as r equal to a, because when you substitute x equal to r cos theta, y equal to r sin theta, it will be r square cos square theta plus r square sin square theta equal to a square, that is r square equal to a square, r equal to a. The line y equal to tan beta into x can also be interpreted as r sin theta is equal to tan beta into r cos theta. R cancels, and you will find that the equation becomes tan theta equal to tan beta, or theta equal to beta will be the equation of straight line which is passing through origin. When we take the radial strip, which will be shown from origin up to the circle in this case, then on strip r will vary from 0 to r equal to a, which is on the circle, and such strips are taken from theta equal to 0 to theta equal to beta. Once we substitute in the given function, that is log of x square plus y square, when you substitute x equal to r cos theta and y equal to r sin theta, this will be simply the function log of r square. And now the given integral can be written as, simply be written as double integral log of r square, that is substitution in the function, and dx dy will be written as r dr d theta, such that on strip r varies from 0 to a and theta varies from 0 to beta. As we write this integral, integration probably is going to be very simple task. One additional thing which we can see about such an integral, the integration which we have written just now has got all the four limits as constant, and if you see the function, then we have got log of r square into r dr, which is to be integrated with respect to r, and we have got a single term called as theta. Now when limits are constant and function is separable, then probably the final answer is going to be the individual integrations multiplication. So I can rewrite the given integral as integral theta equal to 0 to beta d theta, and integral r equal to 0 to a, it is 2 log r into r dr, which can be integrated individually as well as simultaneously. We don't have to integrate with respect to r first or integrate with respect to theta first, as the function is separable. So let us integrate it now. D theta will be integrated as theta between limits 0 to beta, whereas 2 log r into r dr will be integrated by parts, taking 2 as constant, which is outside, and so it will be written as into twice log r is retained, r is integrated as r square by 2, this will be within limits 0 to a, minus integral 0 to a, differentiation of log r is 1 upon r, and integration of r is r square by 2 dr. So it will be within the square brackets beta minus 0 when I substitute limits for theta, into twice, in the first term it will be a square by 2 into log a minus 0, whereas the second integral will be minus half integral 0 to a r dr. Ultimately the answer will come out to be twice beta into bracket a square by 2 log a, and when we integrate this it will be half integration of r is r square by 2 within limits 0 to a. So it will be 2 beta into bracket a square by 2 log a minus a square by 4. Final answer, when we multiply by 2 which is outside, it will be beta into a square, that is a square beta can be taken common. If required, we can take 1 upon 2 also common or 1 upon 4 as common. Within the bracket it will be twice log a minus 1. If we just recall the entire procedure, when we started with the solution, we had the four curves as x equal to y cot beta to x equal to under root a square minus y square, and then y equal to 0 to y equal to a sin beta. We have first of all drawn the region of integration, which turned out to be a sector of that particular circle which subtends an angle of beta with positive x-axis, the internal angle being beta. And when we take radial step, r varies from 0 to a, whereas theta is going to vary from 0 to beta. As we substitute it in the given function, it becomes log of r square, and dx dy will be r dr d theta. So we have written the integral as theta equal to 0 to beta, and integral r equal to 0 to a, it is log of r square into r dr d theta. Log of r square can be written as 2 log r, 2 can be taken outside, and as the limits are constant and the function is separable in r and theta, we can separate the two integrals and evaluate the overall answer as we have done it over here. It was theta d theta that was integrated as theta, and it was between the limits 0 to beta, so integration turned out to be only beta. Whereas in the second case, 2 has been taken outside as constant. Log r being function 1 and r as function 2, we have proceeded to integration by parts, and it was log r into integration of r, which will be r square by 2 within limits 0 to a. Whereas it was minus integral 0 to a differentiation of log r, that is 1 upon r, and integration of r, which is r square by 2 dr. We have taken 2 constant outside. There is a beta value which is coming from integration of theta. So it was 2 beta into bracket. The first term can be very easily written as it was a square log a, I suppose, upon 2, and the second term, when we substitute the limits and integrate it, we got it as simply 1 upon where was it? We got it as 1 upon r into r square by 2 dr. And so r cancels out, half can be taken outside, and again the second integral will turn out to be simply integral r dr, which after integration gives us the value as a square by 2. The overall answer in this case comes out to be a square beta upon 2 into bracket 2 log a minus 1. The problem becomes simple as well as solvable if we switch to the polar coordinates. So we have solved the first problem, which is talking about the radial strips, and now we have a set of 4 problems, and almost all of them are to be solved by taking the radial strips. The first problem is integral minus infinity to infinity. Integral minus infinity to infinity, that is both the inner and outer limits are same, dx dy upon x square plus y square plus 1 bracket raised to 3 by 2. Second, being integral 0 to a, integral 0 to under root a square minus y square, it is sine of pi by a square into bracket a square minus x square minus y square dx dy. Third is integral 0 to 1, integral 1 to under root x minus x square 4xy into e raised to x square plus y square with a minus sign upon x square plus y square dx dy. Whereas the last one is integral 0 to a x e raised to minus x square dx, integral root of ax minus x square to under root of a square minus x square y upon x square plus y square into e raised to minus y square dy. There is a unique thing about all these problems. There is a similarity or a common factor among all these problems, and you can observe that almost all the problems, they contain a term like x square plus y square, and it was the same term that we were having even in the previous problem. X square plus y square indicates that it has to be integrated by taking the polar coordinates if required. It's not mandatory. We have solved earlier a few problems where x square plus y square we have integrated with respect to x or y. But here, when e raised to x square plus y square terms comes into picture, or it is sine of x square plus y square, all these cases should be solved by taking the polar coordinates, that is considering the radial strips. Consider the first problem. When the limits are constant, and in this case both the limits are minus infinity to plus infinity, we need not talk about which is limit of x and which is limit of y, because both the limits are from minus infinity to plus infinity. In general, we can say that we are talking about the entire region, that is all the 4 coordinates or the entire coordinate plane that we have is to be considered. So x-axis, y-axis, origin, and the region of integration is the entire area. Because even if the strip is parallel to x-axis, it begins at minus infinity and goes up to plus infinity, that is left to right fully. And such strips are taken from y equal to minus infinity to y equal to plus infinity. Ultimately, the entire plane is to be considered. In this case, as the given function is non-integrable, because you cannot integrate with respect to x or y first, we will have to convert it to polar form. This particular problem is very important because the region appears to be a rectangular one, but is now getting converted to a circular region, when I can say that this circle is expanding whose radius tends to infinity. Ultimately, the entire plane will be covered by such a circular region, and then when we take the radial strip, on that particular strip, r is going to vary from 0 to r on such a circle whose radius is infinity. So limits of r will be from 0 to infinity, and theta, that is angle made by the radial strip, such radial strips we should be taking right from 0 degrees, and we are required to cover the entire circle. So the total angle or the coverage of theta will be from 0 to 2 pi, that is 360 degrees. And so with the substitution, that we can say converting to polar or transforming to polar coordinates, transforming to polar coordinates with x equal to r cos theta, y equal to r sin theta as the substitution. Therefore we have dx dy as r dr d theta. The given integral can be written as integral r equal to 0 to r tending to infinity, theta equal to 0 to theta equal to 2 pi, 1 upon x square plus y square means r square plus, originally it is x square plus y square plus 1, so it will be r square plus 1 bracket raised to 3 by 2 into dx dy is r dr d theta. If you recall, the situation is quite similar to the previous problem, as the limits are constant and the function is in the separable form, that is r and theta, they can be separated. We can write it as integral 0 to 2 pi d theta, integral r equal to 0 to r tending to infinity, it is r upon r square plus 1 bracket raised to 3 by 2 dr. Now r square plus 1 if differentiated gives us 2r. Out of that r is already present, probably we will go for the adjustment as 2, so that differentiation of the denominator will be present as a numerator. We can rewrite it. Of course, first d theta can be integrated. Integration comes out to be theta between 0 to 2 pi. Whereas the second integral I will write it as from 0 to infinity, it will be r square plus 1 bracket raised to minus 3 by 2 into r dr with that 2 which is adjusted. This is simply in the form integral fx bracket raised to n into f dash x dx. This is the form. And if we substitute fx equal to t, then f dash x dx as a whole will become dt, and this will be integral t raised to n dt, which can be integrated as t raised to n plus 1 upon n plus 1. So using that formula, we can proceed. Of course, limits of theta are substituted, and this integration will be r square plus 1 bracket raised to minus 3 by 2 plus 1 divided by minus 3 by 2 plus 1 within the limits 0 to infinity. And so this comes out to be pi. We have minus half in the denominator, which will go to the numerator as minus 2. Constant I am taking outside. And the term that remains is r square plus 1 bracket raised to minus half, that is 1 upon under root of r square plus 1 within limits 0 to infinity. So this will be minus 2 pi. When I substitute upper limit, it will be simply 1 upon infinity, which will be 0. And the lower limit r equal to 0, when it is substituted, it will be minus 1 upon root 1, which is 1. So this comes out to be minus 2 pi into bracket 0 minus 1, the final answer being 2 pi. So the problem which we were given was containing the terms like x square plus y square or function of x square plus y square. It became the simpler solution and rather a faster one when we have converted the region, that was the entire coordinate plane, to a circle having radius infinity where theta varies from 0 to 2 pi. The entire integration was one of the simplest integral and the final answer was 2 pi. Even in this case we had all the limits constant and the function which was separable. We can separate out the two integrals and the overall answer was the product of the integration evaluation of each of these integrals. Let us consider the second problem. In case of the second problem, when we are given that the limits, inner limits are from 0 to under root a square minus y square, indicating that these are limits in y which are values of x. That means the strips are taken parallel to x-axis. On strip x varies from 0 to under root a square minus y square, and such strips are taken from y equal to 0 to y equal to a. So the four limits that we get over here are x equal to 0, which is y-axis, x equal to under root of a square minus y square, which is nothing but a circle, x square plus y square equal to a square. Outer limits are y equal to 0, that is x-axis, and y equal to a, which is a line parallel to x-axis. To find the region, we will have to draw that circle of radius a, that is one of the boundaries, x square plus y square equal to a square, x equal to 0, that is y-axis, y equal to 0, that is x-axis. We can also locate the points of intersection, a0 with x-axis, 0a with y-axis, and y equal to a line will be now passing through the topmost point. As the strip is parallel to x-axis, it is starting on y-axis going up to the circle, and such strips are taken from y equal to 0 to y equal to a. The region of integration is the quarter of the circle, which is in the first quadrant. The function again cannot be integrated because it is sine of pi upon a square into bracket a square minus x square minus y square, and we cannot integrate it. If we take strip which is in the radial direction, that is by transforming it to polar, probably the job could be simpler because it will turn out to be some function of r square, and we can always adjust 2r dr because r dr d theta will be the substitution for dx dy, and hence we say that transforming it to polar coordinates, which in turn means that we are supposed to take the radial strip, and on that radial strip r will vary from r equal to 0 at origin to r on the circle, and the equation of circle in the polar form will be r equal to a. And to cover this first quadrant, theta will vary from 0 to pi by 2. So transforming to polar, that is x equal to r cos theta, y equal to r sin theta. Therefore, we have dx dy as r dr d theta, and the function that was sine of pi upon a square into bracket a square minus into bracket x square plus y square, actually I am rewriting it, will be simply pi upon sine of pi upon a square into bracket a square minus r square. Limits of integration, as we have already discussed, from r equal to 0 to r equal to a, theta varying from 0 to pi by 2. The given integral can be written as theta varying from 0 to pi by 2, r varying from 0 to a. It will be sine of into bracket pi by a square into bracket a square minus r square into r dr d theta. If we go for a substitution, that is pi upon a square into bracket a square minus r square is equal to t temporarily, then after differentiating the left hand side with respect to r, we get pi upon a square into bracket minus 2r dr is equal to dt. Out of this whole thing, we already have r dr, and so r dr can be written as minus a square dt upon 2 pi. With this substitution, I am not going to find the limits, because now this will turn out to be, in my mind, I can say that it is going to be something like sine of t into dt type of format, which can be integrated to minus cos t. At this level, we need not show each and every substitution. This is the thing which we will be carrying out in our mind and rewrite the given integral. Again, limits are constant, so I can separate out theta from 0 to pi by 2 d theta, integral r equal to 0 to a, sine of pi upon a square into bracket a square minus r square. I will have to adjust the differential of this particular bracket, which we have already calculated, and that differential, when I write it, it will be minus a square upon 2 pi, or a square upon 2 pi can be adjusted. I can straight away write it as minus 2 pi r dr upon a square, and I know that this particular term was not present. I have added that particular term, and so I will have to multiply outside by a square upon minus 2 pi. So this will be in the form sine of fr into f dash r dr. With our usual substitution as fr equal to t, f dash r dr will be dt. We can proceed with the integration. The corresponding constant has already been adjusted. So it will be minus a square upon 2 pi. d theta is integrated as theta between limits 0 to pi by 2. Integration of sine will be minus cos of pi upon a square into bracket a square minus r square within limits 0 to a. We are not going to divide by the coefficient, because that division has already been taken place. This is not a single degree term like you are integrating something like sine of ax plus b. So integration will be minus cos of ax plus b upon a. If it would have been single degree term, that was the adjustment. This is a second degree term, so we will have to actually carry out the adjustment and then proceed further with the solution. Once we reach this point, then we can substitute the limits. It will be minus a square upon 2 pi into the bracket. It will be pi by 2 minus 0. And when we substitute in the second one, of course one more minus sign is coming out, so it will become plus. At upper limit it will be cos of pi upon a square into bracket a square minus a square, whereas at lower limit it will be minus cos of pi upon a square into bracket a square minus 0. As we substitute upper and lower limits, we get the answer in this form. So it will be a square upon 2 pi into pi by 2, that is first term, into bracket it will be cos of 0 minus cos of a square cancels pi. So 1 pi will cancel here. It will be a square by 4 into bracket 1 minus minus 1, which becomes 2. So final answer is a square by 2. One of the typical problems over here, the solution becomes simple and straightforward because we had considered the radial strips. So again a problem with the radial strip. We proceed to the third case where we find that the limits are in terms of x. That means he has taken strips parallel to y-axis. On strip y is varying from y equal to 1 first of all to y equal to under root of x minus x square, and such strips he has taken from x equal to 0 to x equal to 1. So the limits are y equal to 1 to y equal to under root x minus x square, the second boundary, which can be interpreted as y square equal to x minus x square, that is x square plus y square minus x is equal to 0. The third boundary is x equal to 0, that is y axis, and the fourth one is x equal to 1. First of all, we will have to check as what this curve x square plus y square minus x equal to 0 will be. This particular curve is actually a circle, because the general equation of circle x square plus y square equal to 2ax is a circle touching y axis having center at a0 and radius is a. Comparing it, it will be x square plus y square equal to x, and so 2a will correspond to 1 over here, and ultimately it is going to be a circle which is touching y axis, a circle which is going to touch y axis, and its center is half comma 0. Its diameter is 1. So this is the given circle. He is starting the strip at y equal to 1. His strip is parallel to, there must be something wrong. Because if he begins the strip at y equal to 1, y equal to 1 is going to be some point, because this is half. There should be some mistake. This should be from y equal to 0. Should be from y equal to 0. So he is going to take strip parallel to y axis from y equal to 0, that is x axis, to y on circle, and such strips he has taken from x equal to 0 to x equal to 1. And so the region of integration is the upper semicircle of this particular circle, which is x square plus y square equal to x. Now if we are to take strips in the polar form, again there is an indication given by x square plus y square term which is appearing at two places. We will be transforming it to polar and will be taking radial strip. The equation of circle in the polar form will be r square equal to r cos theta, that is r equal to cos theta. And so the given integral after substitution with the standard substitution as x equal to r cos theta, y equal to r sin theta on this particular area will be rewritten as theta varying from 0 to pi by 2, r varying from 0 to r on the circle, and r on circle for the first time is not constant, it is function of theta. It will be 4 r cos theta into r sin theta, it is 4xy, into e raised to minus r square upon x square plus y square is r square, and then dx dy will be rewritten as r dr d theta. Here the limits are not constant, though the function is separable. We are not going to integrate with respect to both of them simultaneously. We will have to integrate with respect to r first, because then the theta term will be again introduced. 4 constant can be taken outside. You can observe that this r and r square will get cancelled with r square that we have in the denominator. It will be e raised to minus r square into r dr, where r varies from 0 to cos theta, into we have sin theta cos theta d theta. We are required to perform this integration first with respect to r. And if I am to consider e raised to t type of integration, then I will have to have its derivative, that is derivative of minus r square present over here. And minus r square when differentiated will give me minus 2r. Out of that r is already there, minus 2 should be adjusted, and we will be dividing outside by minus 2. And so the integral will be minus twice integral theta equal to 0 to pi by 2. It will be e raised to minus r square within limits 0 to cos theta into sin theta cos theta d theta. When you substitute the limits, it will be minus twice theta equal to 0 to pi by 2. It will be e raised to minus cos square theta minus e raised to 0 into sin theta cos theta d theta. We will have two terms over here. It will be minus twice integral 0 to pi by 2 e raised to minus cos square theta into sin theta cos theta d theta as the first integral, and e raised to 0 is 1. So the second integral will be minus minus plus twice integral theta equal to 0 to pi by 2 sin theta into cos theta into d theta. These two integrals are to be evaluated, which we are getting through the substitution. We will have to integrate it with respect to r. That was our previous discussion. We are ending up with some term like e raised to minus cos square theta into sin theta cos theta, and if we are to integrate it, we will have to have the differentiation of minus cos square theta with us, which will be गप बसा नाही तर घरी जावं. उघड दारू उघड, मी सांगतो. हॅलो, ए विलास दारू उघड. विलास दारू उघड. Can't you keep quiet? You are supposed to keep quiet, otherwise come up just 5 minutes before the lecture. बंद कर रे तर. नाही, उघडच ठेव. बोलू देत त्यांना वडा, मग बघतो मी त्यांच्याकडे. पूर्ण उघडून ठेव. सरकवतो पडदा, बघू कोण बोलतंय, त्याला मी घरीच पाठवतो. I said silence, huh? So we have come across the term like 0 to pi by 2 e raised to minus cos square theta into sin theta cos theta d theta. The differentiation of minus cos square theta will be minus 2 cos theta into derivative of cos theta, which will be sin theta. You are again required to adjust 2 over here, because minus cos square theta will result in derivative as 2 sin theta cos theta. Out of that 2 we already have, minus sign will be left outside, and it will turn out to be minus integral 0 to pi by 2 e raised to minus cos square theta into 2 sin theta cos theta d theta. So it will be in the form e raised to f theta into f dash theta d theta. And the second one we can directly integrate, because sin theta's derivative is cos theta, so it will be plus twice sin square theta upon 2 between limits 0 to pi by 2. Integration of the first one will be e raised to minus cos square theta within limits 0 to pi by 2, plus when you substitute the limit it will be sin square pi by 2 minus sin square 0. It will be minus e raised to minus cos square pi by 2, cos pi by 2 is 0, minus e raised to minus 1, that is the first term, plus into bracket sin pi by 2 is 1 minus 0. Ultimately the answer will be minus into bracket 1 minus 1 upon e plus 1. So minus 1 plus 1 will cancel out here and the final answer is 1 upon e.